Good afternoon, everyone. My name is Eric Bishop, and welcome to the International Silicone Conference organized by Rubber and Plastics News. We're certain you'll enjoy the variety of speakers and panel discussions offered throughout the conference. Our speaker this afternoon is Toby Samples. Toby is a staff engineer with Akron Rubber Development Laboratory, and the title of his presentation is Rudimentary Tools to Troubleshoot Your Product, a Silicone Wiper Blade Test Case. Toby is a mechanical polymer engineer with a passion for polymers. He grew up in the rubber industry as the son of ARDL's founder, Bob Samples. As a child, he remembers strolling through the lab, smelling, stretching, and even chewing on rheometer buttons from the waste pile. Toby spent after-school hours in the predictive testing department and gained an excitement for simulation of polymers at an early age. Today, he focuses on custom test procedures, custom test apparatus design and manufacture, data analysis automation, product validation testing, and product simulation. Toby most enjoys the collaborative problem-solving element between him and his customers. With that, I'd like to introduce Toby Samples.
Thank you very much, Eric, for that warm introduction. Welcome, virtual attendees. I know this is different for all of us, and I hope you enjoy this presentation. Rudimentary tools to troubleshoot your product. My perspective involves, as Eric mentioned, a very mechanical, hands-on approach to the final product and characterizing materials up to that point. In this presentation, I have a symbol of a wiper blade wiping a windshield. This will indicate to you whenever there is the wiper blade going through our processes at our organization or through the processes that I'm pointing out in this test case. ARDL is an accredited independent testing laboratory founded in 1962 by my dad, Bob Samples. We are experienced rubber and analytical chemists and engineers with about 100 employees. We're dedicated to continuing investment in technology. Our organization and our forms of expertise are approximately broken down into the categories shown at the right. The wiper blade itself, a silicone wiper blade, has traveled through all these departments in problem-solving cases. And I excluded plastics testing, but maybe in an overmolded test case, it might have been included in problems we've solved. Today we'll discuss a problem solver's philosophy, followed by problem identification in terms of perspective and in terms of being shaped by the capability and resources available from your vendors, you, and your customer. Problem-solving tool belt. This is what I feel is necessary for any rubber technologist, whether you're a materials engineer or a mechanical engineer or a design engineer. Creative solutions with minimal and no time budget. Likely in your R&D scenarios at this day and age, you're still facing limited time and limited budget to deal with. And I'd like to show you how to get through one solution using this tool belt. You don't need to be the best. Surround yourself with the best and know who to talk to. From picking around in the molding department at our organization as a child, my dad would tell me this. He said, you just need to surround yourself with the experts and know exactly who to talk to. At that point, I knew communication was critical. He would speak to each person differently in terms that they could understand the project or the part of the problem that they were involved in. With that being said, problem identification is very related to perspective. Polymer problems can be categorized in these four categories from when I field calls: material selection, performance prediction and prototyping, product performance evaluation, and failure and contaminant analysis. My expertise lies within the central two categories here. And I also consider myself an expert in finding the exact person to talk to. Even being a vendor, I like to listen to my vendors and what they know for material selection, as well as failure and contaminant analysis. With you at the center of this, you know your perspective best, right? So we look at our coworkers, our vendors, our customers for sources of information. Mine can be categorized that I face every week as a material supplier, a manufacturer or inventor, an end user or litigator, a competitor or consultant. they're broken up into these separate regions very specifically by what kind of information they hold and what value they can add to the problem set. The problem formats with regards to description, recipe, green stock material, slab material, the product, and the unknowns are broken down as follows from my material suppliers. I love listening to material suppliers' requests for quotations because they offer simply process descriptions or partial established or parametric recipes. In their voices, they express their marketing goals and they express the market they're trying to address with this new material. They allow us to play an imagination game with it. The tests we can do, if they're not simply standardized, we can customize something to perhaps be custom to the exact product market they're targeting. Manufacturers, inventors, they're less entertaining, not so much a imagination game when a manufacturer and inventor addresses a problem, but they have very specific specs, sketches, photographs, CAD, ideas, goals, and process descriptions all laid out. And often it's a matter of translating their ideas, their goals, their specs right into the service. End users and litigators, again, allow me to jump into the imagination game. They come to you with a photograph or a regulatory requirement addressing something, maybe a unique product had an issue. Maybe a silicone product choked their dog, or they're just trying to figure out how to address a certain regulatory requirement that there's a runoff and it's breaking certain regulatory requirements. Competitors are also in the form of manufacturers or inventors, but they come with a more dramatic sense to their approach. They have a photograph and a goal and a process description with the goal of overcoming or presenting a better unique value proposition than their competitor. And they will have that one product that they say, this is what we got to beat. I love that dramatic pressure from our manufacturers that are trying to compete in the industry. Consultants, they often are the third or fourth party in a discussion about problems. Consultants simply give you a list of the specifications that you would like to address, and they have very little information that they're willing to share about the product itself. And that's typically when I return with a spreadsheet of lists of, this is the 100 pieces of information I need, because you only have about one chance to communicate with the consultant's firsthand user of the material, the problem we need to address. And you got to get that right the first time. With regards to capabilities and resources, starting with you are the person you know best in your capability and resources. Every 1 to 2 years, I think it's healthy to write down your soft skills and your hard skills and identify in the rubber industry what you can do to help make the processes go along faster. I feel with my concise communication, I can help whittle down a project just so that each of the departments or the customer can understand the problem and its solution and the way we get there. Likewise, your organization should provide feedback and checking, directives, and team building. Continuing education, funding, and equipment is also critical to problem solving. The tool belt I was referring to. I feel that every technologist and every organization should make these available to their engineers or anyone making a design decision or anyone trying to validate a product. Modular fixturing. Modular fixturing such as T-slot rails are fabulous in positioning your product so that you can impose a load on it, or you can flex it and hold it and then switch it up for the next product. Universal test machines in my office, I have this model right here, this Instron 5500. With that modular fixturing, you can create quite a unique apparatus for any goal you'd like to achieve, whether it be compression or stretching in a certain way, or even torsion on a material you can achieve with the universal test machine and an offset axis. Manufacturing tools. These engineers and technologists also need subtractive manufacturing tools such as CNC mills and need to familiarize themselves with it. And then additive manufacturing, these 3D printers consumer grade 3D printers, such as the one shown here in my office, is all that you really need for some small scale prototyping and also fixturing. ABS is printable on these, and that gives you a nice rigid substrate for squishing soft materials such as some of the softer silicones. On the E&M, or electromechanical and digital side of prediction, prototyping, and evaluation, I think the technologists should also be familiarized with microcontrollers and low-cost computers, as well as, if you're not a programmer, I'm not a programmer, I recommend you familiarize yourself with a programming language in which you can take a physical analysis from a load cell and convert it directly into a useful data. This programming language symbols I show here are a Python symbol. That's the Python programming language, and C++. Python is probably the easiest language to learn. And with that, you can do full stack programming. Full stack is with regards to commanding a Arduino, for instance, here, commanding an Arduino to tell a motor to start driving in a certain direction. On the end of that motor shaft, you may have a cam which activates an actuator. The actuator could be pushing down on your seal and do cyclic pressures. And the feedback you're getting from that is time versus displacement, for instance, or time versus load, and you can do sort of relaxation experiments on that. Low-cost computers, this has a footprint of about 3 inches by 4 inches, unlike a PC, in which you can have a lab bench set up with many experiments with a low footprint. CAD and FEA software are becoming more ubiquitous. I feel that all engineers need some sort of package. A lot of my customers use a SolidWorks add-on package, which is affordable and has some limitations compared to the more full-blown packages, but it's sufficient to do some hyperelastic simulation. Right here in this image, this is the neck of the wiper blade that I'm about to discuss as the test case. I was given the task for this project to innovate on the wiper blade. It was a very broad problem statement, but I had to take some perspective. The perspective I chose to take is that of an end user. How can I look at a wiper blade innovation without addressing a problem? The problem I address is wide streaking and chattering. I may be a little bit cheap and unwilling to change my wiper blades. I believe they're suggested to be changed every 6 to 9 months, but I feel that wide streaking and chattering is an issue with new blades and expired blades alike. Converting that problem statement of I don't like wide streaking and chattering into an engineering hypothesis, I came up with this. I would like to address the pressure distribution non-uniformity through a novel use of additives. At Ardell, we have a molding department, and we have lots of servo-hydraulic systems, and we also have the capability to characterize a material for use in finite element analysis. That characterization usually involves 3 or 4 tests, which can give you a good picture of how your material deforms. Those can be fit to a mathematical model and input to a finite element analysis. So this streaking I'm discussing, it kind of looks like this. Maybe you're familiar with it. At one end of the wiper blade, or sometimes dead center, there's a 3 or 4 inch wide strip that makes you crick your neck when you're driving and look under that unwiped section of the blade. That's what I'm trying to address here with the non-uniformity of pressure distribution. To plan my experiment, my 2 questions were, can I vary the long-term compression relaxation response? And 2, not grossly affect the quasi-static stress-strain behavior. So the question 1 is dealing with viscoelastic or time-dependent properties. The second question is dealing specifically with the mechanical deformation, the hyperelastic deformation when you apply a monotonic load, a single load on a wiper blade. The variable in this case, I knew our molding department was working with a few proprietary additives, so I worked with a no loading, low loading, and high loading instance. The baseline, I purchased two most expensive silicone wiper blades to compare in the same test apparatus I was devising. The base wiper compound that we're working with has none of this proprietary additive in it to start with. To answer question one, method one was to come up with a custom apparatus. Whenever I devise a custom test apparatus, I model it off of a standard such that there's a basis and something you can reflect upon throughout the process of developing and validating your procedure. ISO 3384 and ASTM D6147 both refer to an experiment called CSR, an automotive procedure typically used in the automotive industry, called compression stress relaxation, in which you compress a button, you hold on it at a set deflection, and you monitor the reaction force. That tells you, gives you a good sense of how a seal will perform with respect to time. I converted these specifications to something I call a continuous wiper stress relaxation, where you simply flex the blade against the windshield and hold it there at set deflection. When holding it at a set deflection, you can monitor the reaction force and see if it would lift up in a stress sense or a reaction force sense, and therefore wipe less and more poorly. That was my perspective of what could be causing this streak of wiping where it's leaving residue on the window. This second question was, how do I address that it's not adversely affecting other parts of the wiper blade performance? In that, you use finite element analysis of the experimental setup. I performed uniaxial tension, pulling on a dog bone, pure shear, pulling on a high aspect ratio sample, and equal biaxial tension, pulling radially in all directions, and volumetric compression, or constrained compression, shoving on a cylinder in a constrained cylinder. Again, the steps were to mix and mold wiper blades with 3 sets of additives, along with my 2 purchased blades, verify no unintended mechanical effects with FEA, and then test using this continuous wiper stress relaxation experiment, and compare the consumer blades to the new blades. Utilizing this tool belt I had mentioned, my finite element analysis software makes you create a mesh in it. So you discretize, or you break up the solid into small parts. Wonderfully, those same meshes are great to be used with a 3D printer. They also need a discretized form of the solid. So in parallel, I devised a 3-inch fixture to hold a wiper blade. This is the finite element, a 2D model of the wiper blade. The stresses here are shown in this tiniest neck region. Those were the highest stresses experienced in this. Again, using this DIY sort of approach for this R&D experiment, I used my CNC machine to just locate some holes in a piece of extruded aluminum channel. I also purchased a load cell for $12 with its corresponding signal amplifier, HX711 signal amplifier, that was for $12 combined. And I calibrated that using my universal test machine, making sure that the 6 kilograms had a full scale calibration. Here you see the benchtop rat's nest of wiring, where I was able to both read the load off of the load cell, have an indicator light for the experiment upon completion of data acquisition, and record and broadcast that data to my PC. I'm trying to impress upon you how important it is to take advantage of these cheap, small footprint pieces of technology for just finding one piece of information that's critical to moving forward your R&D, your product development, things of that nature. Here, this is the 3D printed fixture that I designed in ABS. It holds the blade with a very light load, trying to simulate the end of a blade, whether it's the bottom or the top, that may be lifting off a little bit and causing this excess of residue on the windshield. Here, the blade's being pressed on the load path. This aluminum bar here represents the windshield. This load path travels through the load cell and into the fixture here, with the wiring going back to collect load values versus time. The second question is addressed with the finite element software. Again, this was the model to start with, FEA Model 2D. These are very simple to make, and they also process very quickly in the FEA processor when you simplify your use case in seals or in extruded elastomers down to a 2D case. The no additive, low additive, and high additive use cases showed very similar peak stresses. So that didn't seem to be a concern for me that it was being adversely affected by adjusting this additive loading level. The CWSR results. In this continuous wiper stress relaxation experiment, again, the wiper blade was pressed down on the windshield or the bar of aluminum. And over time, for 24 hours, it was observed how much of the load decayed. 100% at the beginning. And in the case of the base formulation, with no additive, 60% of the residual load remained. With half of the additive added, it was 63%. And in the maximum loading, it was 85%. So I was able to positively affect how much force is retained in pressing this wiper blade against the windshield. The two consumer grade blades were at 75% of the initial retained force and 79% of the initial retained force, which shows me that likely by adding as much as I did of the additive, I'm most likely adversely affecting something that I can't perceive with this simple experiment. In this, I used, again, Python to acquire the data and to acquire these time points of load versus time. Looking ahead, the next step is to simply mold the production blades. In our molding department, we were able to mold those blades and then apply them into these wiper test bucks, in which we would do dry and wet experiments. You get a qualitative wipe quality, and you can also do this winter slap test, in which, growing up in Ohio, we're often used to trying to shake that ice off your blades and to see if this additive affected the durability of those blades. There's also a low temperature wipe test that shows how well the blades are able to clear broken up ice particles from your windshield. That's up next in this experiment, and I hope to get to that soon. But I sure wanted to get these R&D experiments out of the way with low cost options rather than doing these high capital intensive experiments afterwards. Thank you very much for the opportunity to discuss this with you, and I look forward to any questions you may have.
Toby, thank you very much for the presentation. That's a lot of work that you guys did, and very impressive. I think your capabilities could be applied across a wide range of industries in the silicone world. So thanks for putting that together and for presenting it. I do have some questions for you, if you're willing. First question I have is, where do you draw the line between a DIY testing approach and or validated or accredited methods internally and externally?
Thank you very much, Eric. It comes down to time, money, and when you want to move on to an approval body. So if it's internal R&D and you're just trying to push your product to that next level, this could be just enough. However, if you need to prove it out before making that next level of purchase decision, then I highly recommend that you first simplify it down to maybe a uniaxial test case. For instance, with seals or for instance, a current project I have is for an immersion creep apparatus, where you're dangling from a medical device in a saline solution that simulates body fluids. And at first, we did that with, as I showed there, we did that with Arduinos, load cells that were very cheap. Or excuse me, it was a creep experiment. We did that with a web camera to observe the strain as you dangle a weight from it. And we also used aluminum materials, so things that could corrode in the saline environment. once that was proved out, we made the level to go to that 10x final design and made everything out of titanium. And instead of a low-cost Arduino, we moved on to PLC and a excuse me, a Toughbook, which is a PC that could take the saline environment. So it's just a matter of prototype and then find out when you're ready to make that final step.
Sounds good. Thank you. Have you otherwise developed any custom tests for silicone products?
Yes, for planning for this show, it was an exciting endeavor. I was given these by you, these wonderful baby nipples.
Yes.
And we were going to do a workshop. And in that workshop, I wanted to carry everyone through the step of, if you don't have the CAD images, how to cross-section and reverse engineer. Pretty simple bed scanner and some sort of calibrated measurement next to it. And I wanted to present an abrasive fatigue crack device for it. And before knowing that there was a pandemic coming around, I had a set of my teeth cast for them.
Oh, really?
Yes. And this was going to be a fatigue experiment hooked to a linear actuator in which we were going to gnaw on that pacifier cyclically. So it would involve a jawing motion like this.
Sure.
That my smile could be the standardized smile for pacifier fatigue testing, and using these same tools, these rudimentary tools, to get a very sophisticated answer.
Well, that's a little bit frightening, and to think that your teeth are certainly much larger than those of a typical infant who'd be using the baby bottle nipple, but that would be certainly a worst case scenario, I think. One last question. Toby, what resources do you suggest for technologists who may want to apply these basic tools?
So this is where it comes down to how I acquired these. I acquired most of this with my own pocketbook, save for the Intron. And I recommend that. Go through the pain of buying a few of these things on your own if you have the least bit of interest in getting into programming. That way you know that the pain behind spending a little money to get the R&D going. It's fabulous to have these microcontrollers, and you can do simple samples of data and load acquisition, and really start with YouTube. One thing about Ardell's mentality with our expertise is that we give so much free advice. So call us up, email me, and I'd be happy to address anything. Just don't be afraid if you get a quotation thrown at you in the endeavor to try to get free advice. But I encourage you to come to our material selection advisors, or for me, if you want to do any sort of custom testing. And these, I typically create these fixtures and send them to the customer so they can continue to do it in-house.
Super. That's wonderful. Well, it's a great resource, and I certainly would recommend anybody contacting you or consulting with you.
Thank you.
Toby, I can't thank you enough for joining us today. I'd also like to thank our audience for attending this session of the International Silicone Conference, and thank you to our sponsors for supporting this conference. If you want to revisit this session or any others from the conference, they will be available on Rubber and Plastics News website. That's rubbernews.com after the event is completed. And don't forget that you can connect with your colleagues here through the virtual networking program, which can be found on the left-hand side of your screen. Just simply click the Meet icon to start connecting with fellow attendees. So thank you again for joining us today. Toby, thank you again for presenting. And I hope that you will return at 3:30 p.m. Eastern to view Rick Ziebel's comprehensive paper on third stream additives that modify LSR properties. Thanks for being here. Take care, guys. Bye-bye.